Hi everybody. In this video, I'm going to talk about Bernoulli random variable. So there are some common pre-named random variables in probability theory, and these pre-named random variables are fundamental in probability theory and statistics. They are standardized probability distributions that model specific types of random variable. They serve as building blocks for more complex model and help describe many real-world phenomena. These include the Bernoulli random variable, binomial random variable, Poisson random variable, normal, exponential, so on and so forth. I will provide an overview of all these random variables, beginning with the Bernoulli distribution. So let's start with Bernoulli random variable. So the Bernoulli random variable is named after a Swiss mathematician, Jacob Bernoulli. It's the simplest type of random variable modeling a single trial or experiment with only two possible outcomes. These outcomes are mutually exclusive and exhaustive. An experiment with two possible outcomes, therefore, is called Bernoulli experiment or a Bernoulli trial. Example, flipping a coin. You cannot get both the outcomes at the same time. Either you will get a head or a tail, and union of both the outcomes makes the sample space, which makes it mutually exclusive and exhaustive. So this is an example of Bernoulli random variable. A yes or no question or a true-false question. Testing a product. You either pass it or you fail it. Okay, so all these are the example of Bernoulli random variable, and you have only two possible outcomes in it. So the Bernoulli random variable records the result of a single trial where one outcome is identified as success and the other as failure. Now let's define the Bernoulli random variable X. What is random variable before that? Let's review the definition. So in probability theory, a random variable is formally defined as a function from sample space to the real numbers. Now for a Bernoulli random variable, sample space contains only two outcomes, success or failures. We assign numerical values to the outcome to quantify them mathematically. The conventional assignment is assigning value 1 to success and 0 to failure. And this assignment is arbitrary, but widely used due to its simplicity and intuitive nature, because the one can be thought of as yes or something occurred, while 0 represents no or did not occur. But note, you can even encounter different assignment. For instance, some people like to assign value 1 for success and -1 for failure. This can be useful in certain mathematical model or when symmetry around 0 is desired. Okay, so now let's define the probability mass function, and we will go by the conventional assignment that X takes value 1 when it's a success and 0 to failure. So let's define the probability mass function. The probability mass function gives the probability that the random variable takes on each value. So let P denotes the probability of success in the experiment, then the probability that X takes value 1 is P, and probability that X take value 0 would be 1 minus P. Since we have only two outcomes and both are mutually exclusive, if probability of success is P, then probability of failure would be 1 minus P. And since P is the probability, therefore P would be between 0 and 1. Okay, now this PMF can be written in a compact or closed form as well. And the closed form for the PMF for Bernoulli random variable is P to the power K times 1 minus P to the power 1 minus K. And K can take value either 0 or 1. And P is the probability of success. And clearly, if you take K is equals to 0, you get P to the power 0, that is 1. And you get 1 minus P to the power 1 minus 0, which is just 1 minus P. Which means that if X is equals to 0, then its probability is equals to 1 minus P. And similarly, if you take K equals to 1, 1 minus P to the power, you'll get 0, which is equals to 1. And you'll just get it to be equals to P. Therefore, probability at X equals to 1 would be equals to P. And the support of this random variable X is 0 and 1. So the support of any random variable is defined as the possible values that random variable can take. And here, the Bernoulli random variable can take value either 0 or 1. Now remember, if somebody assigns different value to X, then the support of X would change according to that assignment. For instance, if somebody assigns -1 to failure and 1 to success, then the support of x would change to -1 and 1. Perfect. So such a random variable is said to be a Bernoulli random variable. The only parameter needed to describe the probability distribution of the random variable is p. That is the probability of success. Now we have the PMF, and it's time to find the CDF, which is the cumulative distribution function. So the CDF of a random variable x is given by probability of x less than equals to that small x, that value. Okay, so now x can take, the support of x here is 0 and 1. So let's see what happens when this small x is less than 0. So the CDF of any value x, whenever x is strictly less than 0, will always be equals to 0, because the probability of the random variable at any point strictly less than 0 is equals to 0. Therefore, the CDF of x at any point strictly less than 0 would be equals to 0. When this small x is between 0 and 1, 0 included, 1 excluded, the CDF of x would take value 1 minus p. Basically, if you take any number which is greater than equals to 0 and strictly less than 1, for instance, you take 0.5. And if you try to find the CDF of x at 0.5, so basically you are trying to find the probability of the random variable x less than equals to 0.5. And now you know that at every other point except 0, the probability of the random variable is 0. And at the point 0, the probability of this Bernoulli random variable is 1 minus p. Therefore, if you take any point between close bracket 0 and open bracket 1, the CDF at that point would be 1 minus p. If you take any value greater than equals to 1, the CDF in that case would be equals to 1 minus p plus p. Why? Let's take x is equals to 1. Let's try to see what would happen if you take x is equals to 1. So the CDF at 1 would be probability of x less than equals to 1. That means you're adding the probability of the random variables at all the values less than equals to 1. You know that the probability of this random variable is 0 for all the values except at the point 0 and 1. And at 0, it has probability 1 minus p, and at 1, it has probability p. So you add those two probabilities and you get the probability, you get the CDF at point 1. Now, if you take any point greater than 1, still the CDF at that point would be 1 minus p plus p. Because at all the other point, the PMF is actually 0. Therefore, if you simplify all these things, you get that the CDF for any value strictly less than 0 would be 0. The CDF between 0, included 0, and strictly less than 1 would be 1 minus p. And if you find the CDF at any value greater than equals to 1, you get 1. Time to find the expectation. Now we know that expectation of any random variable is defined as summation of k times probability of that random variable at that point k, where summation is taken over the support of that random variable. Here, the support of the random variable is basically contains only two values, 0 or 1. So you basically take k equals to 0 and you multiply it with the probability that random variable can take value 0 plus 1, and the probability that random variable can take value 1. So you will have 0 times 1 minus p plus 1 times p, and it will give you p. So expectation of a Bernoulli random variable would be equals to p. Variance, we know that the formula of variance is expectation of x square minus expectation of x whole square. We already know the value of E of x, so we only need to find the value of expectation of x square. Okay, now what would be expectation of x square? Expectation of x square is basically summation k square probability of the random variable at point k, and we are summing it over again the support of x. We know that support of x contains only two values, 0 and 1. Therefore, we get 0 square times the probability of x at 0, which is 1 minus p, plus 1 square times probability of x at point 1, which is equals to p. We simplify it and we get that E of x square is equals to p. We have the value of expectation of x square. We have the value of expectation of x. Therefore, we get that variance of x would be equals to p minus expectation of x square, expectation of x is equals to p. So we get variance is equals to p minus p squared. You factor out p and you get that variance of Bernoulli random variable is p times 1 minus p. Now, the standard deviation of a random variable is defined as the square root of the variance, and it's a practice question for you all to find the standard deviation of Bernoulli random variable. An important note that Bernoulli distribution is fundamental in probability theory and statistics, and it serves as a building block for more complex distributions, such as the binomial distribution, geometric distribution, negative binomial distribution, Poisson distribution, so on and so forth. So it's very important to have a better understanding of Bernoulli random variable. So that's all about Bernoulli random variable. We'll see an extension of this distribution in the next video.